So I wanted to talk a little bit about one of our last topics on iteration methods for linear systems. And this is going to be the conjugate gradient methods or biconjugate gradient methods. And I'm not going to introduce too much about what they do, except I will walk through the algorithms. And then what we're going to do is a little demonstration on Matlab and the use of these in Matlab. And also show you some of the functionality that these iterative schemes offer you in terms of looking at its convergence properties, dictating the iterations, dictating the convergence itself. So I will certainly highlight that as we go through this. Okay, so first of all, let's talk about it from the point of view of an algorithm. And I'm going to go ahead and share screen here. And the algorithm, kind of interestingly enough, is here we go. Start here. The algorithm itself starts off with some initial guesses. So this is the idea. You're going to start off with you're going to solve Ax equal to b. You're going to start off with an initial guess, which is here, x naught is equal to 0. And what you'd like to do is you pick a residual. You guess a residual, which is going to just be b itself. And then you pick this other vector p, which in some sense is going to look a little bit like the search direction in gradient descent. So that's why it's called gradient or conjugate gradient methods. Okay, so we're initially going to pick the p to be r0, which is b. So this is our initial guess. Remember that in some of these kind of algorithms like Jacobi or Gauss-Seidel, if you have a strictly diagonal dominant structure, you're guaranteed to converge no matter how you guess this. So, but these are the initial guesses. And then you go into the loop. So the first thing you do is you start to pick a direction to search in. So the idea here is to take R0 transpose R and P0 transpose A P0. So notice that this P0 transpose A P0 looks a lot like the Rayleigh quotient, right? So it's projecting onto that matrix A and giving you a direction. And then what you do is you approximate the solution. X of n is your current value plus this alpha value times the P. And you take a step. And then with this new value, you calculate the residual. The new residual is the old residual plus, here you go, you calculate A acting on P of n times alpha of n. So this gives you, in some sense, a step in the residual direction. And then you look at the improvement of how you've done. Remember that R is sort of supposed to be like your residual, so you can compute your R of n, transpose R of n, versus R of n minus 1, R of n minus 1. So presumably as your Rn is getting better, this beta n is getting smaller, right? So that's the idea, is that you should be improving, and then you change your search direction. Your P of n is what the R of n is, times this B of n, P of n minus 1. So it's kind of defined as just an algorithm that if you kind of spend some time and you dissect back what these things are doing, you can make sense of each of the steps in terms of a search for a solution. So this is it's called conjugate gradient descent. And so this is part of what you want in terms of looking for solutions in iterative structure. A more a broader class of this is when you have you're just searching and your solutions can be complex and there's no restrictions on the matrix A, and this is called biconjugate gradient descent. Very similar, but instead of working with just R and P, we're going to actually work with two sets of vectors, P0, R0, Q0, S0. And this is how you pick them. So the P0, R0 are just like before with B, and then Q0, S0 are arbitrary. And notice what we're going to do here is we're going to have left and right multiplies in this algorithm. So you're going to define a length again for the iteration step, which is now, though, projection onto S and Q, which are these arbitrary vectors. And again, forming some kind of inner product with a Rayleigh quotient. And then you update your values. X of n is what it was before, plus the search direction times P of n. Update your residual, update your S of n, B of n, P of n, Q of n. So you just update them and just iterate progressively. And each of these sort of has a little bit of the structure like a gradient descent, but now it's this using this dual vector spaces of the Q's, Q, S, P, and R0 to search in this space. And notice that you have complex conjugation explicitly in the algorithm. So this is kind of the structure. There's actually a lot here of details, again, that we are not going to get into around gradient descent methods or biconjugate gradient descent methods. What we're going to do really is just come back to thinking about Matlab and implementing this in Matlab. So without further ado, what I want to actually do is talk about two algorithms in Matlab that implement these things. One is the GMRES, the generalized method of residuals, which I talked about in the last lecture. And now this one is, and also I'm going to talk about biconjugate gradient stabilized method, BICG STAB. So it's like what the algorithm, second algorithm I just showed you, except for there's some stabilization steps in there as well. So these get quite complicated, but again, remember, all of this is aimed at beating the bottleneck of order n cubed, right? So that's our bottleneck that we're going after. How could I solve an ax equal to b for a very large system faster than order m cubed? Because if that's what you're solving it in, it's extremely slow, especially for large matrices. All right, so with that in mind, let's go and go ahead and start looking at some Matlab here. So I'm going to share screen and I'm going to program in Matlab. All right, so here we are. We're in Matlab and we're going to start programming this. The first thing I want to do is just do a help GMRES. So that's the command we want to look at. So here we go. So GMRES. So bring it to the top here. Generalized minimum residual method. So GMRES, all you do is say, if I have a matrix matrix A and a B, I have an AX equals to B. I put A and B here, it gives me a solution X. In fact, notice what it says, attempts to solve the system of linear equations, AX equal to B, okay? So that's what you're gonna go after, is you're gonna actually go ahead and put this in, and it's gonna iterate using that GMRES algorithm towards trying to iterate towards solution convergence. I'm going to give a very bad example of this here. I mean, oftentimes when you structure these matrices A, like I made a comment in class, A oftentimes is large and diagonally and has sort of almost a diagonal dominant structure, so that the iteration procedure converges very quickly. And you'll see here when I do this, it takes quite a while to converge for just some generic matrix A. I also want to highlight some of the functionalities you get out of GMRES. It's all listed here, but you can take GMRES, and let me come down to here, and you give it A and B, and this is this line of code right here, right? So you can give it options. You can have it restart. In other words, it's going to iterate a certain amount of times and stop, and you can restart it, okay? You can specify the tolerance, tall. In other words, once my solution gets within 10 to the minus 4 or 10 to the minus 5 or 10 to the minus 10, the default's 10 to the minus 6, it will stop. And then max it is the max number of iterations. So the max number of iterations, the default's 10. So it's going to take 10 iterations. So that's not very many, right? That's not going to get you too far. So notice that it's assuming then that you actually are close to the solution if you're going to try to get a solution within 10 iterations. And so there's reasons why that would work, because oftentimes you're solving this AX equal to B where B changes slightly. So you have a solution for AX equal to B and B changes slightly. So all you need to do is update that solution. So you use your previous solution for this. And this often happens when solving partial differential equations. There are other options. You can even bring in what are called preconditioning matrices. And one of the things I'll say about this is, again, we've, in some sense, barely scratched the surface of all the innovations in linear algebra and numerical methods for linear algebra. You were starting to get into the very sophisticated things for solving large-scale systems, but oftentimes there's this idea of preconditioners that can be brought in, which is ways to transform these matrices to make them a little bit more amenable to the iteration process. And finally, one thing very important here is when you do this, you can also specify x0, which is an initial guess. Remember the initial guess here, it'll just start with zeros. So this has no knowledge of a solution, but if you're already close, in other words, you're solving this and you have a solution x equal to b and b changes slightly, you can actually say, take that old solution, plug it in as x0 and iterate from there. So in other words, you're very close to the solution and your iteration now can just take that close solution and then make it more accurate. Okay, so that's the inputs that you have available to GMRES. What about the outputs? Well, the outputs can give you a flag. There are different flags that come out of this thing, right? So, you know, if the flag is 0, it converged. Or if 1, then it went through the maximum number of iterations and didn't converge. There's some other ones here about ill conditioning of preconditioners and so forth, okay? But really what I want to do is let's come back to here because I want to show you this. These are the outputs because we're going to look at these. I'm going to get the solution X. I'm going to get that flag out. I'm going to get the relative residual. So this is going to give me essentially what my error is. So once I've stopped converging, it's going to tell me what the error is. The relative residual is going to be after I stopped iterating, here's your error. Iter is the number of iterations. It says here's the relative, so it's going to tell you what the error is, and the iteration is like maybe it took you 52 iterations to get to where you are, and that's the error. And resvec is a very interesting one. The resvec is a vector of the residuals, and we're going to take a look at that. In other words, it's going to keep track at each iteration of how you're doing. And so we're going to explore that one a little bit because that one's actually kind of fun to look at to see how rapidly the convergence happens for these algorithms. All right, so let's come back to here and let's define a matrix. I'm going to first make this thing 100 by 100, so it's not going to be very big. This is just really just to play around with GMRES, okay? And I'm going to say that the matrix A is going to just be some rand matrix, which is m by m, and the B will be some rand vector m by 1. And I'm going to go solve this. So, so first of all, let's call it the truth. The truth will be, let's call it x star, which will be a backslash b. Okay, so that's my truth. And so I solve this just basically without iteration. I've just solved it exactly using, LU. If it's a square matrix, it's going to do LU decomposition and solve that. Now what we want to do is solve it with these iteration techniques. So let's call that X. Simple as this. There it is. Done. I have the solution. So in fact, let's look at the solution and compare it to what the exact answer is. So what I'm going to do is I'm going to make a plot here, subplot 2, 1, 1. And what I'm going to do here is plot a bar of x star. So this is the values of all the x values of that vector, which is x is a vector of 100 components, and that's the truth vector. I'm also going to plot what comes out of GMRES. Okay, call that x. And the question is, of course, that you'd want the solutions to match, right? So check it out. I run, and there they are. And you can see they're different. And in fact, the bottom one, which is your iterated solution, is pretty far off, in fact, from the exact answer, which is x star. So why is that? Well, first of all, it didn't go through very many iterations. So it's maybe not surprising. And so we're going to have to take a look at that. But I'm also going to just compute the residual, right? I'm going to say, well, what is AX minus B? Call that R, and let's get that number. So when I run this, there's that. And oops, I want the norm of this, sorry. I want the norm of the residual. So how big is the norm of the residual? The difference between that, and it's pretty big, 10, okay? And notice, by the way, it's giving me an error here. So the residual is big, so it's not even close to the solution. And it says GMRES stopped at iteration 10 without converging to desired tolerance of 10 to the minus 6. And of course, it's obvious that it did that. All right. So let's go ahead and take a look at what we can do with this. Okay, so let's go back to help GMRES and look at some of the options and look at some of the flags. So first of all, if I want to go through more iterations, there it is right there. It's this component. So I look at A and B, I put in A and B. Let's say I don't want to do anything with the restart and the tolerance. So then I would leave those as empties, and then maximum iterations, I could put something in. So I can do GMRES, and I put these as empties, which is the tolerance, right? And as well as, what was it? Sorry, it was the tolerance and the restart. And I just tell it here, how about 100 iterations? Okay, so now I'm going to run this. Okay, so actually that looks a bit better, doesn't it? Look at that. That's these are starting to look pretty similar. In fact, now check it out. The residual is 10 minus 14. Okay, so I just needed to iterate longer. Let's do it again. Remember, every time I do this, it's a random matrix. There we go. Look at that, 100 iterations, and I got it. So what happened? Well, now I'm iterating quite a bit more. So instead of just 10 iterations, which I didn't converge, now I'm doing 100, and this thing is converging. Okay, let's do some more diagnostics. In particular, if I come back to here, oops. And by the way, look at what it says here. GMRES converged at iteration 100 to a solution with residual 0. Great. So let's do help GMRES. Okay, and let's pull this thing off. And I want to start looking at all of this stuff. So I want to start getting some more diagnostics out. So let's copy and paste this over to here. And I don't like having all these as, let's do this. Copy this here. And I'm going to call that X. And we'll just leave everything else capital X. But all right. So now I'm going to do the same command, but now I'm going to pull back all of these extra quantities. The flag, the relative residual, the iterations, the resvec. Okay? So I'm going to run this again. And what we're going to do is, again, take a look. There I am. I've converged to the solutions with 100 iterations. The residual is 10 minus 14. And what I'm going to plot now is make a new figure. And there's some things I want to look at. So first of all, we can look at relative residual and iterations. So that's going to be, so let's look at iter first. So it went all 100 iterations. So in other words, it didn't stop on the way in there. It just went all the way through to the maximum number of iterations allowed. And by the way, the rel-res, relative residual, this is relative residual, not just what I had written down. It's 0. So, you know, it's not this here what we computed, which is just how well is it, what's the norm of AX minus B. So a little slightly different measure, but does a pretty good job. The more interesting one to plot is, let's plot the resvec. And let's make that line width 2. And so what this is going to show us is this vector of residuals as it's iterating along. Oops. Oop. Oh, sorry, it's all has to be capped. Sorry. There we go. Run. And there it is. Okay, so there is what you're seeing. This is how this thing iterated to the solution. So it's an iteration procedure, and what you're seeing here is the relative residual at each step of this iteration as it goes through. And notice how it sort of dives down here around iteration, right at iteration 100, it just pops way down. So remember, I go through iteration 100 iterations. So at 101 is the last iteration, and notice how it just basically tanks to 0. Let's actually maybe bring this up and say, let's only go through 80 iterations run. So now look at that. So now it's 80 iterations. Notice how the error keeps dropping. So it's finding better and better approximations to the vector X as it goes. And of course here, it didn't quite do it, right? It took 80 iterations. It's not down as small as I'd like it to be, right? Or as small as we'd like it to be. And if we go to 200 iterations, then it's basically stops here, and then we can say iter. So I don't actually know why. So it stopped at 100 iterations, it seems. All right, set max to 100. All right, so anyway, the iterations is 100. So basically, it basically got the solution there for us after 100 iterations. Now, in this case, it took 100 iterations to get to our solution, right? So it's not necessarily saving us a lot of time. Let's actually go up, but here's the deal. Like when you start doing bigger and bigger matrices, see, now it's taking, look at it. This is actually not dropping to 0 very quickly, by the way, right? And in fact, the solutions, well, iterations. Oop. So, all right, let me do screen share again here. Share. Okay. I hope this is still recording. All right. Last thing we're going to do is we're going to turn our attention now then. So that's anyway, that's enough on that one. Let's go to help BICGSTAB. This is the, let me go up here. This is the biconjugate gradients stabilized method. So it's very similar. All you do is replace BCG GMRES with BICGSTAB. So basically you're going to come up here and say x is equal to, let me pull these out, x is equal to BICGSTAB. And then you put A, B. So now we can do the same thing we did before. I'm going to comment this out. And I'm going to bring this back down to a 100 by 100 matrix, and let's run it. Run it. Oops. Something went wrong. All right. So why am I getting that thing? Let me go. Okay. Something's a little funky here. Let's go back to read about here. And with BICGSTAB, right, it's giving you an approximation to the solution. Put in A, put in B. It's going to try to go find a solution. You can specify a tolerance. There's a tolerance. You can also specify maximum iterations, which is right there, and preconditioners. And also, just like before, you can guess an initial solution, right? So this is the idea behind what you would do with BICGSTAB, okay? And then you can pull out all the same things as before, right? So a flag, relative residual, iteration, and resvec. So we're going to pull all those out here, where we're going to just basically copy and paste this here. And let's just make sure they're all the same. Resvec, iter, so you get flag, relative res, iter, resvec. Flag, relative, resvec, and then now you say BICGSTAB. AB, and let's go ahead and now what we want to do is, I think I was giving it I was actually, so notice that it's a little different structure, tolerance and max iters. And I had put M to be 200, so it's probably why it was screwing up. So let's just go through max iterations, 200. Okay, so we're going to run this, and then we're going to plot our solutions. And this is not making sense. So I'm not sure what's going on, guys. Let's plot the relative resvec, see what's going on with that. All right, so there's the resvec. So notice what it's doing, and then I think it's actually crashing on us here because this thing here, notice how it goes to 40 some iterations, and I gave it a maximum number of iterations. Actually, let's go get a max number of iterations, 200. Let's run it and see what happens here. So there's the resvec. Okay, so there's a problem. So this BICG stab is not having a good time here. Look at this. It's just, this is as iterating, it's actually doing worse and worse and worse. Okay, and partly because it's not finding a good direction to search in and get the solution. And so a lot of these algorithms are basically made for certain structured matrices. Notice this is 10 to the 4. So this is not doing a good job converging at all. So I could take this random matrix A and then add some large diagonal element. So let's do I m by m, for instance. So that's going to add ones on that diagonal. Okay, and still poor. Let's make it larger. See what happens here. There we go. See, like I made it strongly diagonal dominant by putting a big diagonal down there. And now notice that the solution is starting to converge. Look at this. It just takes these big jumps. And if I zoom in here, it's starting to converge. So you see that what I just showed you is BICG stab actually does not work well for just some random matrix, whereas GMRES did okay. However, BICG stab is really good when you have some of these diagonal matrices that often show up in computation, scientific computing applications. And there you see what it's doing, right? It does a wiggling around and then it pops in towards the solution. And so obviously it doesn't, so in other words, these iteration techniques really are relying on the fact that that you have some kind of structure to these matrices. These iteration techniques are not generically good for saying, hey, here's just some large matrix A with no structure. Oftentimes it's large matrices with some kind of structure. BICG stab, I just show you, it keeps breaking for just some random matrix, but as soon as I make it sort of having a diagonal dominant structure, gets the solution right away. And that's kind of just inherent in a lot of these iteration techniques. All right, so anyway, you can play around with these. There is a lot of power in those methods, and they're just there at your fingertips. And there's also a lot more to know about these iteration techniques when you go to large scale computing. And so I encourage you to just kick these around when you can. And anyway, that's the lecture on these iteration techniques. And hopefully you can play around with the code.